Today I want to talk about a very interesting problem. The problem is the following. Suppose that one wants to use the following limit, the limit when x goes to 0 of sine of x over x is equal to 1. This limit, all it's saying is that if x is a very small number, the sign of that very small number is very similar to the number that you use to get the sign of. The idea is to make use of this limit together with facts like the sine of pi half is equal to 1 to somehow get an approximation for pi. How can we do this? Well, the core principle is that the sine of pi half is equal to 1, and also that there exists a formula for the sine of half an angle, and this is essentially expressed in terms of the cosine, and this is 1 minus the cosine of x over 2. Right. So given these two facts, one can imagine that we could start making a descending ladder of smaller and smaller quantities based on pi half, things like pi half. Then we can build the next term, which would be pi over 4. Then we can build the next term, which would be pi over 8. And for all of these angles, we always know exactly what the sine of that angle is, right? Because we can always go into the formula for the sine of x half and plug it in and get a value, get an exact value for the sine of pi over 4, for the sine of pi over 8. So the core idea is then, well, what happens if we attempt to take this limit through this sequence? What happens if we attempt to take the limit of x being very small? Because as you see, each term is actually half as large as the next one. As the previous one. So in principle, this sequence converges to 0 in the limit. When we do infinite amount of steps. So the idea is, well, what happens if we take this limit along this line, along the lines of pi half, pi over 4, pi over 8, all the way down to 0? Well, for each one of these terms, we will know exactly what the sign is. And since we know that this also approximates the argument itself, what we're going to have is for a generic term, what we would have is x pi over 2 to the n. And since we know that this is approximately equal to the argument, we would have a very precise approximation of pi. So okay, let's get to work. The main result of this is going to be a closed formula for the sine of some argument, which I'm not gonna constrain it to be only pi. I'm gonna leave it open to be any x, and just what we're going to be interested in is in finding formulas for things like sine of x over 2 to the n and the cosine of x over 2 to the n. And these as expressed in terms of the sine or cosine of x only, and no other things, right? So I'll actually concentrate first on the cosine because it's easier, and it's actually pretty straightforward, right? So the formula for the cosine, and the reason why it's easier is because the cosine is actually expressed in terms of the cosine itself, while the sine is expressed in terms of the cosine, which means that this ladder is actually a little more complicated for the sine because it refers to this cosine you might think of is actually the square root of 1 minus the sine square. So this fact makes it a little harder to write this expression. It's also possible, and we'll do it, but it's slightly more complicated. So for the cosine, it's actually more straightforward, because for the cosine, the formula is as follows. Cosine of x half is equal to square root of 1 plus the cosine of x over 2. Right. So for our formula, for our desired formula of cosine of x over 2 to the n, I'm gonna propose something, and what I'm gonna propose is, well, I'm gonna propose that this is actually Bn, and I'm going to define Bn right here. Bn is going to be defined as follows. Bn is equal to the square root of bn minus 1 plus 1 over 2, while b0 is simply the cosine of x. It's very easy to check that this is actually true. You can, for example, if you attempt to check this for n equals 1, this is actually just referring to the formula on the left, right? Because all it's saying is that if you are attempting to get for n equals 1, this is x over 2, it's saying, well, this is b1, but what b1 is b n minus 1, so b0, so cosine, plus 1 over 2. So it's just saying this formula, right? And you can see that this actually had nothing to do with the fact that the x was referring to the b0. This actually follows. Like if one wants to get x over 4, what we would have to do is, well, takes the result for x over 2, add 1 to it, divide by 2, and take the root. And this is what this sequence is there for, right? What this sequence is doing is, well, if you want to compute b2, you have to take b1, add 1 to it, divide by 2, and take the root. So these, this actually holds. Okay, so now the statement for the sine of x is going to be slightly more complicated, because the sine of x over 2 to the n, this actually, the statement that holds is the following: 2 to the n times sine of x over 2 to the n divided by the sine of x is equal to an. And what an is actually, an is equal to the product of, from L equals 1 to n, to n of 1 over bn. Right, so let's prove this. The way that we will prove this is by induction. So how does the induction principle work? The induction principle has to prove something by induction. You have to do two things. You first have to prove this for a base case. You have to prove that the statement is true, that it is true for some base case. For some base case. Right? In our case, the base case will be n equals 1. We'll do that in a second, but first I'm going to state what else we need to do. The other thing we need to do is we need to assume that it is true, but not a true for all n. Assume that it is true for n smaller than k. For all n smaller than some k. And now what we have to do is given this assumption, given the assumption that it is true for all n smaller than k, we have to prove it. We have to then prove it for n equals k. Okay, so let's get to it. Let's attempt to prove this for n equals 1. So for n equals 1, what our formula says is 2 to the 1 times the sine of x over 2 divided by the sine of x is equal to a1. But we also know that since a1 is the product from L equals 1 to n of the bn's, of 1 over the bn's, this is actually 1 over b1, right? We remember from before what the b1 is essentially 1 plus the b1 is computed in terms of b0, so it's 1 plus the cosine divided by 2 root of that. So okay, so we can say, and we know what that is. That is essentially the cosine of x over 2. So okay, so what this is saying is that this is equal to 1 over the cosine of x over 2. Right? Right, okay, perfect. And then, well, what we need to do is we need to work on the left hand side then. What I'm going to do is I'm going to write this as 2 times. I'm going to use the doubling sign formula. And what that formula says is, I'm going to do it over here. I'm going to write it down over here, is that the sine of x is equal to twice the sine of x half times the cosine of x half. Right? Perfect. So what this means is that this is equal, this left hand side is equal to 2 times the sine of x half divided by twice the sine of x half times the cosine of x half. And the 2 sine and the 2 sine cancel, and we get what we wanted, right? So we get this is indeed true, right? These two are the same. So now, to complete our proof by induction, we need to assume that it is true for all n smaller than k, and then prove it for n equals k. Okay, so what we would do is we will evaluate this for n equals k and make use of the fact that it is true for every n that is smaller than k, to prove that it is true for n equals k. So okay, let's evaluate this statement, the left hand side of this statement for n equals k. The left hand side is 2 to the k times the sine of x divided by 2 to the k divided by the sine of x. And here what I would do is I will rewrite this in a way. I will make use of 2 things. I will make use actually of only one thing. I'm going to split this into 2 times the sine of x half times the cosine of x half. And then I'm just gonna shift. I'm gonna redistribute the 2 to the k's in the following manner. So I'm gonna do 2 times 2 to the k minus 1 times the sine of x half divided by 2 to the k minus 1. Now we also have in the denominator a 2 that cancels among these two. Well, I'm going to do it later. 2 times 2 the sine of x half times the cosine of x half. Right, perfect. So okay, the first thing is the cancellation between these two and these two, and then here's the key part. Notice that I can go ahead and rename this into y. Right. So here you can see that I also have the same y, and I have also the same y. But I'm going to concentrate on the part that has the 2 signs. I'm going to concentrate on this part, this whole block, these, and these also with the sign. Okay, so this part, what is encircled in blue is actually this statement, the correct statement for n equals k minus 1, right? See, it has 2 to some power sine of something divided by the same power that it's multiplied by, and dividing there is the sine of that same thing. So this whole blue box I can substitute using my assumption. I can substitute it by AK, right? So perfect. I'm going to do that. What I have on my left hand side is AK minus 1. But here's that one. I'm going to write what's left. there is also the cosine of x half. But what is this AK? I'm gonna examine this more closely. What these AK are is actually, I have 1 over the cosine of x half product from L equals 1 to the k minus 1 of 1 over BL. And remember that B0 was the cosine. Which cosine? Well, if you follow, what should actually be here is cosine of y, which in our case is x half. Why? Well, notice that this whole ladder started here. B0 is cosine of x, right? So it's the cosine of whatever was in here. So it's if the sign is down here, it's the cosine of that, right? So the starting point for this sequence is actually cosine of x half, and since I'm going from L equals 1, I'm actually what I'm dividing by is actually the next term, is the cosine. So B1 is essentially is actually equal to the cosine of x over 4. So okay, so and this is the first term that I have here. So I'm multiplying all the terms from B1 to k minus 1. So what we could do is we could do the following. Well, we could say I'm gonna shift the indices in the B's. I'm gonna define as CLs, and what the CLs are essentially the following. CL is gonna be exactly the same as the BLs. It's gonna be defined as 1 plus the CL minus 1 divided by 2. But my B here, remember the B's are defined in the same way, but B0 is cosine of x half. Now what I'm gonna do is I'm gonna say Z0 is actually cosine of x. Why do I want to do that? Well, because then what actually happens is all I'm doing is I'm essentially shifting the indices. C1 is now B0. C2 is B1. So all I did was, with this redefinition, this sequence is essentially the same as the B's, but it's just defined with twice the argument, essentially. What it's doing is essentially shifting the indices from the B's into the C's. Perfect. But what that means is, okay, now this whole multiplication is actually equal to the product from L equals 1 to k of 1 over the CLs. Perfect. So what do we know by now? What we know by now is that 2 to the k is equal to sine times sine over x over 2 to the k divided by the sine of x is equal to the product from L equals 1 to k of 1 over CL, where C0 is defined as the cosine, not the sine, the cosine of x, while the next terms are defined recursively by 1 plus the CL minus 1 divided by 2. And this is exactly what we needed to prove. And so the key point here was that the B0s were, this sequence was always referring to the y, was always referring to the argument that we had in here. So this sequence that we had here, even though it looked like the form that we wanted, it looked like this, like a product of BNs, it was not rooted on the same point. It was rooted on cosine of x half. So what we needed to do is we needed to shift it, and essentially this term was contributing the missing term. The very first term that we were missing was being added by this cosine of x half. Right? So, okay, then now we know that this is true. Now we want to make use of this fact that we just proved to, together with the fact that the limit when x goes to 0, of sine of x over x is equal to 1. In reality, what we would do is we would take the limit when n goes to infinity of sine of x over 2 to the n. Right? The argument is going to 0 as n goes to infinity. So this limit is not different than this limit. So this is still 1. This is still 1. So 1 is equal to this. But now we can plug in our formula for this guy, right? Our formula for this guy is this formula, is whatever the 2 to the power is, I'm gonna get this product of CLs up to that point. So perfect. So what we do is we evaluate. So this is that. I'm gonna put the limit, and now we also get an overall factor, the sine of x, and this is just this denominator that we get, times an divided by x over 2 to the n, and we also get times 2 to the n. Right, we get that extra 2 to the n from the formula itself. So the 2 to the n's are actually cancel among each other. 2 to the n's cancel. And we can finish this by essentially solving. I'm gonna solve for this x down here. So I'm gonna place it on the left hand side, and I'm gonna say x is equal to something. The something is the sine of x times the limit when n goes to infinity of an. And this is the core formula. I'm gonna shift variables in the next later, but this is the core. This is the core formula. And as I said, the ANs are a product of BNs, so the ANs are a product of BNs of 1 over BL, and this is from L equals 1. And also remember that B0 was cosine of x. And the B0s are defined recursively. Yeah. Okay, so okay, I'm gonna shift variables. What I'm gonna do is instead of referring to B0 as cosine of something, what I'm gonna do is I'm gonna shift this into B0. I'm gonna make the following shift. I'm gonna say, well, B0 is actually my variable, is my y, right? So perfect. So this is my desired variable. So now the sequence is B0 is y and b, and so these did not change. The way the b's are defined recursively is not changed. It's 1 plus bn minus 1 divided by 2. What is changed are these things, right? For example, sine of x. Well, notice that B0 was our cosine, right? So now sine of that, so previously what was sine of x, one can also write this as the square root of 1 minus the cosine square of x. And since I'm calling that cosine y, this is going to be 1 minus y squared. So that gives us a rule for this sign that I have here. But also the x on the left hand side is now this x that we had on the left hand side is now actually arc cosine of y. So what we get in the end is the following formula. We get a formula for the arc cosine. What we get is that the arc cosine of x is equal to square root of 1 minus x squared. I'm shifting back into calling this x, n equals to infinity of a n. Here comes a n to n 1 over BL. B0 is equal to x Bn is equal to the root of 1 plus Bn minus 1 divided by 2. I just shifted variables. And this is the important formula. So this formula is essentially the formula that will that does what we wanted. Okay, so now we want to make use of this formula we just found to find some approximations for pi. The first approximation for pi we will find it by using x equals 0. By using x equals 0, we can evaluate both sides of the equation. The left-hand side of the equation gives us that the arc cosine of 0, well, that is equal to pi half. And also we can evaluate it using the left-hand side of the right-hand side of the equation. Using the left-hand side, we get this is the root of 1 minus 0 squared times the product. This product from L equals 1 of 1 over BL to n. Right, so we know B0 is 0, B1 is the square root of 1 plus 0 over 2. This is 1 over root 2. B2 is going to be equal to the square root of 1 plus 1 over root 2 over 2. These I'm gonna change. I'm gonna multiply both the numerator and the denominator inside of the fraction by 2. Inside of the root by 2, so this would be 2 plus root 2 over, so this would be this root on top over 2. Right, and actually I can also do the same here, and if I do, what I get is it's root 2 over 2. Right, so actually the final result is that pi half is equal to 2 over root 2 times 2 over root 2 plus root 2 times 2 over root of 2 plus root of 2 plus root 2 times and so actually I can find some particular approximations. So for example, if we only consider this very first term, well, this is not a really good approximation. This would be 1.4142, which is approximately root 2. So okay, that's I mean we know what this value is. At 4 decimals, this would be 157.07. At 4 decimals, so okay, we're quite off. Now if I consider the first two, so if I consider these two factors, these two numbers, what I get is actually 1.530707, and if I consider all three, I consider all these three, the value that I get is actually 1.5607. And the next, which I didn't write the next term, but the next on the sequence is actually 1.5701. So okay, it's clearly approaching our limit. Well, of course we know it converges because we just proved that this limit is true. So now let's make use of a different x to evaluate pi. We will use x equals root 3 over 2. for which we also know what the value of the arc cosine is. The value of the arc cosine for root 3 over 2 is pi over 6. Then, okay, this is the left-hand side. The right-hand side gives us 1 minus 3 quarters. So this happens to be 1/2 times the product of, let's write it as a proper product, L equals 1 to n 1 over BL. But now B0 is root 3 over 2. So B1 is actually the root of 2 plus root 3 over 2. And B2 now happens to be the root of 2 plus the root of 2 plus root 3, all that over 2. And so we get our approximation for pi. What that approximation is that pi is approximately equal to, well, it's exactly equal to this infinite sequence, 2 plus root 3 times 2 over 2 plus root 2 plus root 3 and so on. And as before, I can show you what a couple values for this are. So the first value is obviously just 3, but the first non-trivial value happens to be 3.1058. The next one would be actually 3.1326, and then the next one would be 3.1393, and the fourth one would be 3.1410. Okay, so this also seems to be working, and this actually works for all x. As a final remark, I'm gonna rewrite this expression in a slightly different manner that will also be helpful. What I'm gonna do is I'm gonna concentrate the x dependence on the left. So the x dependence, well, obviously there is an x dependence on the b's, but the separable x dependence, like this one. And then I have this is equal to L equals 1 to infinity of 1 over BL. And for those of you who know a little bit of calculus, this left-hand side actually looks a little familiar, because what these you might know that the derivative of the arc cosine of x is actually minus 1 over 1 minus x squared. So what we have here is essentially minus a function times its derivative. So there is another way to write this, and the way is, well, we can say that this is minus 1/2 the derivative of the arc cosine squared of x. Right, because this derivative would be twice the arc cosine times its derivative, and the 2's cancel and the minus cancels as well. So great, but this isn't helpful unless the left-hand side can also be written as a total derivative of something. Well, it wouldn't surprise you to know that this is actually possible. Otherwise, I wouldn't be telling you about it. And the way to note what that is that if you remember what the fractions look like, where these look like a multiplication of infinite fractions, where these fractions essentially look like 2, then 2 plus twice the initial arc cosine that we were saying. Remember, well, here we started with 0, so it was twice 0, and then it was twice the previous value. So it is a bunch of nested roots that look like 2 plus 2x and things like this. So great. So, well, I'm just gonna ask what is the derivative of this generically? So the derivative of this is 1 over 2 plus root of 2 plus 2x. times 1 over, now we need to evaluate the internal derivative, that is 2 over 2 plus 2x times 2, because the final internal derivative. Okay, so we get a sort of expression that looks very similar to the one we had, right? For if we evaluate an expression like this one that has 2 plus signs, we get an expression that has 2 roots in the denominator. So it seems like this is approximating the term for n equals 2. And this is indeed the case. For if we were to evaluate these with 3 plus signs, we would get a term that has 3 roots in the numerator, and are exactly the roots that we were seeing in these type of expansions. So what I can say then is that the right hand side, this product from L equals 1 to n, essentially, I'm just gonna take some finite n of 1 over BL. This is actually equal to some derivative, and the derivative is going to be the derivative with respect to x of what? The thing that we need to evaluate is 2 plus the root of 2 plus the root, and then we have a bunch of roots. How many? Well, the important thing is that we have n plus signs, n pluses, n plus signs, and then of course these will only, as we saw, this was giving us the correct denominator structure, but we were, first of all, the b's have actually 2's in the numerator. If you remember, what we were getting were actually these expressions, but with 2's in the numerators. Now we have 2's in the denominator, so it wouldn't surprise you to know that we are off by a factor of 4 to the n. There's a factor of 2 per BL, and there's also a factor of 2 because every time we took a derivative, we gain a 1 over 2, which we didn't want. But there is a final factor of 2, which is this factor of 2 that was coming from here, from the final internal derivative, and this factor is there, so we need to divide by it. Right. So what we get in the end is that minus 1/2 the derivative with respect to x of the r cosine squared of x is equal to 1/2 times the limit when n goes to infinity of 4 to the n times the derivative with respect to x of the root, this root. Where there are n plus signs. So to finalize this, what we need to do is we need to integrate this equation. And the good boundaries to integrate these equations are, well, we can cancel these 2's. So good boundaries to integrate these equations are to use from 1 to some indeterminate y. And you'll see, because if we evaluate this for 1, what actually happens in this sequence is that we get, so if we take x equals 1, what we get here is 2 plus 2. This is a 4, so this is root 2. So this is a root 4, so this is 2, and this is actually added to the next to the next 2. So this whole sequence actually it's fixed. It doesn't matter how many plus signs you get. This whole structure is fixed at 2 for x equals 1. So that's why it's good to evaluate it at x equals 1. because it doesn't matter what the value, how many n's there are, we get the same value. This is in the lower limit of the integral. In the upper limit, we get something that depends on y, but the lower limit is fixed. Okay, so but on the left hand side, we can evaluate everything, and on the left hand side, so we have the integral of the r. We have the r cosine of x. This is squared, and this is prime. So this value is minus, so this is actually the lower limit minus the upper limit. So the lower limit is the r cosine of 1 minus the r cosine of y. Perfect. The r cosine of 1 is 0, right? Because it's the value for which the cosine is 1, and that is identically equal to 0. And we now evaluate the left hand side, the right hand side. The right hand side, as we just said, is going to be what? This right hand side would be after the integration. This would be the limit when n goes to infinity of 4 to the n times what? Times these roots. So the root, so it's the y limit minus the 1 limit. So the y limit is just all these roots. This is 2 plus 2 plus 2 plus 2y, but the 1 limit, as I said, is 2, because it's fixed. Once for y equals 1, this limit is fixed at 1. It's all, it doesn't matter how many pluses you have, this is always going to be 2. So another way to put this would be to say these are cosines are actually square. I don't know, unless this is squares. One way to put this, another way to put this is to say that the r cosine squared of y is equal to the limit when n goes to infinity of 4 to the n times 2 minus this structure. Two plus 2y. Okay, so now we can make use of this formula to also approximate pi. So for example, we can use y equals to minus 1, for which we know that the r cosine is exactly pi. So this, the left hand side is pi squared, the r cosine of minus 1 squared, pi squared. And I'm gonna evaluate it for some particular n. Let's say we evaluate it for n equals 2. So this limit for n equals 2. What this limit says is this is 4 to the 2 times 2 minus this root, and this root with 2 pluses. That's what the n means. So this is a 2 plus 1 plus 2 plus 2y. But 2y is minus 1, so this is exactly 2 minus 2. So this is 0, and what we get is 16 times 2 minus root 2, and you can check that this is actually 9.3725. I mean, it's not too close to pi squared, but I mean, it's only the n equals 2 term. To summarize, in this video we found two different ways of writing the r cosine in terms of first products. In terms of the products of these 1 over these BLs, which was found by using the limit when sine of x over x goes to 1, and we just then used it to develop this formula. The second one was essentially just integrating integrating this formula by noticing that the r cosine, that its derivative shows up on the right hand side, and what we end up with was the following formula, which was a formula for the r cosine squared. And with these two formulas, we were able to find different approximations for pi, this one from the product expansion and this one from the limit expansion. So that would be it for this video. I hope you liked it, and see you on the next one.